Hello and welcome to this video on credit risk. For this video I planned the following. First of all, I would like to talk about what risk is. Then I would like to specify this definition and go into some credit risk. Next, we're going to talk about how to measure credit risk, and we're going to apply the discriminant analysis and the logistic regression to build up some credit rating or credit scoring model in R. So, what is risk? A risk is nowadays defined as a deviation of the actual result from the expected result. That is what we call a deviation risk. If you look at this probability distribution, and the middle of this distribution is our expected result or expected value, a deviation risk is the risk of a deviation from this expected value. Accordingly, we can use something like a variance or a standard deviation for the measurement of this risk. But there's also another view in which risk is understood only as a possible negative deviation, what we call a downside risk. So we only see a negative deviation. Generally speaking, the risk can be differentiated into the probability, which is an area under the risk distribution, and the severity of a risk. So the severity is the size of the deviation here. Both, of course, can be managed separately. So we can manage the probability and we can manage the severity. Let us go into some terminology and notation of credit risk. What is credit risk? Credit risk is the danger of the deviation between expected and actual success due to unplanned reduced debt servicing capacity of debtors. So there are different types of credit risk. First of all, the default risk, the risk of partly or completely losing the outstanding debt. Second, the creditworthiness risk, the risk of a worsening in the value, in the present value, of a credit or bond due to not complete but only gradual loss of the ability to service debt, which is expressed, for example, in a deteriorated credit rating. So, if you want to sell such a credit to another person, he will not be willing to pay as much as before if the credit rating of the creditor of the debtor here is deteriorated. A special risk is the counterparty risk, which is a special case of the aforementioned. The difference lies in the fact that default or change in creditworthiness does not affect a borrower, but the counterparty of a derivative transaction. In markets characterized by uncertainty and information asymmetries, every granting of credit involves a credit risk. Since the name-giving credit business is one of the origins and traditional focal points of credit institutions' business activities, comparatively good information and related measurement and management concepts can be found there today. The modern perception of credit risk is the differentiation between expected and unexpected losses. Expected losses have to be part of the pricing in credit business and therefore are a component of the offered interest rate of a credit institution. If the credit institution or any other lender misprices the credit risk, he or she has to face adverse selection problems which will lead to credit losses. Unexpected losses have to be covered by equity, since, complete markets assumed, they cannot be part of the price. Any competitor with enough equity could sustain from including unexpected losses into the interest rate and, thus, could offer cheaper credit at the market. So, what is the aim of financial analysis and credit analysis then? The aim of the credit analysis is the assessment of the personal and economic circumstances of a potential borrower in order to assess the risk associated with granting a loan, or more specific, the probability of a default. The result of this creditworthiness check serves as a basis for decisions on whether to grant the loan and, which is even more important, under which conditions. The question of credit conditions is a very important topic in a bank analysis. If a bank estimates the loan conditions too inaccurately, the effect of adverse selection occurs, because the bank does not recognize the loan defaults in accordance with the principle of causation justice. Here is a simple example. Let us have Bank A. Bank A grants credit conditions regardless of the creditworthiness of the borrower, and thus a flat rate loan. Bank B, on the other hand, grants loan as far as possible dependent on the creditworthiness, i.e. the expected losses of a loan. Customers with a high creditworthiness are paying low loan conditions. Customers with a low creditworthiness pay high loan conditions. Following this formula, the expected loss, EL, of a credit agreement is composed of the probability of default, which is a probability between 0 and 1, the loss given default, LGD. Loss given default is typically the borrowed amount, but there are certain cases where the borrowed amount has to be forecasted, just like in credit lines that will be exhausted before a loss event, something like that. And the exposure at default, EAD. The exposure at default is of course dependent on the securitization of the credit. The probability of default, PD, must be assessed using a rating system. Let us come back to Bank A and to Bank B. And let us have a look at this chart here. We see credit risk rising on our x-axis and the interest rate offered by both banks, Bank A and Bank B, on the epsilon axis. We see Bank A or Bank 1 here offering a flat rate. So independent of the credit risk, they offer just one interest rate. While Bank B or Bank 2 does a risk assessment and offers cheaper credits for low credit risk consumers and high interest rates for bad debtors. So, since Bank A does not take care of the cause-related allocation of loan defaults, it will offer bad borrowers good conditions. Bad borrowers are here and they get good conditions compared to the other bank. And good borrowers, bad conditions. So we have good borrowers here and they got kind of bad conditions compared to the other bank. This automatically benefits Bank B, which is now pleased about an influx of good borrowers. We see the customers switching their banks here, and they have an influx of good borrowers, and they will have an outflux of bad borrowers to Bank A. Since now bad borrowers aggregate themselves with Bank A, here, this bank will suffer substantial defaults in the credit business. Sooner or later, this bank will have to change its business or it will leave the market. As a result, from the adverse selection problem, banks are keen on having the highest possible precision in their credit rating system, since it is clearly a strategic advantage. Of course, we have to mention that the structuring and analysis of financial statements and current interim figures will not be sufficient to get the whole picture. For example, we have to do additional management analysis, future-oriented analysis of the industry situation, examination of submitted short and medium-term business plans, and an evaluation of the private asset situation in the case of individual companies and commercial partnerships, or in the case of existing shareholder guarantees that has to accompany the financial analysis. Especially the assessment of management cannot yet be carried out schematically or statistically. The age, resilience, health, professional competence, and personal integrity of the owners or managing directors of the client company and the experience gained so far in the course of the business relationship are put to the test. Also important are the business culture, the working atmosphere in the company, like frequent fluctuation in staff or even of executives, smooth organizational processes, especially in accounting and controlling. Possible succession problems must be dealt with at an early stage, especially in the case of companies geared to the personality of the entrepreneur. Integrating all these aspects into the credit rating process and integrating due processes in the banking business are still a venture for both scientists and practitioners, and of course it opens up room for further research. Let us now come to statistical methods for credit rating, and first of all we have a look at discriminant analysis. So we have to differentiate with univariate discriminant analysis that is not used anymore, but it's a good starting point to explain, and multivariate discriminant analysis, MDA, which is still not in use anymore. Nevertheless, it's also a good starting point to explain. So, what do we see on the first picture here? We see defaults in relation to equity ratio. So we see on the x-axis the equity ratio, and since we know the higher the equity ratio is, the more stable will be the company. So, measured the equity ratio, let's say at the beginning of a year, and noticed if this company will survive or has survived that year, you will find something like this. So we have two histograms in one picture. We have the blue one with those companies that have survived the year, given the equity ratio at the beginning of the year. And we have a second histogram, the red one, for all those companies that went bankrupt during this year, given the equity ratio at the beginning of the year. And we see that a low equity ratio here leads to many defaults, while a higher equity ratio seemingly helps to survive. And with the red line and the blue line, we see the mean of both histograms. Of course, we can turn this into some probability density functions. Please do not wonder about why now the red curve is higher than the blue curve. This is just because here we only see probabilities, while here we see frequencies. But still, the mean of the defaulted companies and the mean of the non-defaulted companies are at the same point. Of course, we can define some kind of cutoff point. So let's say we take this dashed line here in the middle. Maybe there where those two plots intercept, and we just give credit to those having an equity ratio higher than this point, while we refuse to give credit to those with a lower equity ratio. So that is the most simple strategy in univariate discriminant analysis. Not necessarily we need to take this point here where those two probability curves intercept, but we can also go lower or higher depending on the credit cost. So for example, we take this line or take some other line. Maybe we refuse some more credits or we refuse some less credits depending on the risk involved and the severity, of course. Multivariate discriminant analysis considers several influencing factors and their mutual interactions. So not only the equity ratio that we still have here on the x-axis, but maybe also the current ratio that is now on the epsilon axis. And indeed, equity ratio and current ratio are able to explain most of the default risk. And with colors, we now see the same number of observations here, but red we see those that have not defaulted, and true we see those that have defaulted, so in blue here. Now the idea of multivariate discriminant analysis is to define a line, which is the Z line, and to define Z scores that give us an idea about the risk of default. So this line has a so-called Z score of 0, and all points below that have a higher Z score, and all outside here have a lower Z score than 0. So this is a discriminant line that differentiates between those that are creditworthy and those that are not. Let us now switch to RStudio, and I show you in some clicks how that works out. Okay, first of all, I would like to show the data underlying this analysis. And I have this little Excel file here on my screen, and I would like to show the data that is in this Excel file. So we see 1000 observations, and we see some vectors, so variables. So this is total assets, tot.s. Here we have the equity, here we have the debt, here we have the current assets, here we have the current liabilities, and here we have if the company is defaulted in this year or if the company is not defaulted in this year, given all those numbers at the beginning of the year. Okay, now I have arrived in RStudio. I have lots of code here, and I just would like to lead through this code. First of all, of course, we have to import the data set financial reports XL as X. To do so, I load the library readXL. For those of you who have not installed this library before, please use the install.packages and in brackets and high comma the readXL. I don't need to do that, that's why I put it into the commentary here. Now the second line is just a file.choose command that opens up this file.choose or open file window, and I just need to watch on my desktop, and on my desktop I will find somewhere there's Fin Reports, and I open Fin Reports. Okay, now I have saved the path, only the path, not the whole data, in the variable path. So file.choose, this open dialog window, just gives back the path. And now I put this path into dir name, so I get back the name of the directory, and I set the working directory on that directory. So my desktop is now my working directory. And with a readXL command and with a path, I now read in the financial reports that I'm going to save into my data frame. Now here I have the data frame, 1000 observation and 7 variables. Here we see the variables, and with a double click, or alternatively with the view command with a capital V, I can have a look at the data. It's the same as we saw in Excel. Of course, we first have to calculate the financial ratios because they were not given in the Excel file. So we have to calculate the equity ratio by dividing the equity by total assets. And we have to calculate the current ratio by dividing the current assets by the current liabilities. In this line, I remove all non-complete cases, and now we see that we have 993 cases left, because obviously some of them had some NAs in or nulls in or whatsoever, but now we have clean data. So, I have already showed all the plots that are produced here. I just go down to the linear discriminant analysis. And we're going to apply the mass library. So we have to run the mass library using the library command. I just do that. If you have not installed the mass package, just use install.packages to install it, but I don't need that because it's already installed on my computer. Now, the command to start a linear discriminant analysis is LDA, linear discriminant analysis. And I try to explain the default by, and here we need a little tilde, by the equity ratio and the current ratio using the data df.finreports. I just run this one and I print out the result because the result is saved in a model data type, and I just print everything that is in this data type. So what do we see here? Here we see prior probabilities, how often, how many observations are false and how many are true if it comes to default. So 9.1% are defaulted, 90% survived. Here we see the group means. Those who have not defaulted, so false, have an equity ratio of 32%, and a current ratio of 83, 0.83. Those who have defaulted have a negative equity ratio, so of course they have defaulted, and a much lower current ratio. And here we see the coefficients of the linear discriminants. So those values that we need to calculate the Z values. I can now use this model to do predictions. So I can put those Z values to my data. I just do that. And I just now put the classes to my data, the predicted probabilities of a class membership, and the linear discriminants. And we now take a look at this data. We now have 12 variables because, of course, we have the equity ratio and the current ratio that we have calculated before. We have the predicted class, which is false in many cases. We have the probabilities of being part of that class, and here we have the Z-score added to the data. Now, to put things together, the separation line is determined by the so-called Z-score. The Z-score is merely a weighted sum of the key figures used in the analysis. The weights are determined by the MDA. The procedure used for this is very similar to the OLS regression. The optimization rule is maximize the ratio of between group sum of squares to within group sum of squares. So the Z-score is just a weighted average of the financial ratios. So the Z-score has a value of 0 on the dividing line. It is therefore clear that companies with a certain score value are at risk of insolvency. So, which it is depends, of course, on the variables used in the linear discriminant analysis, of course. In R, the MDA determines group means and computes for each individual company the probability of belonging to the different groups. The individual is then affected to the group with the highest possible score. The LDA command output in R contains the following elements. Prior probabilities of groups, the proportion of observations in each group. For example, there are 90.8% of the training observations in the solvent group and 9.2% of the training observations in the insolvent group. Group means shows the mean of each variable in each group. And the coefficients of linear discriminants shows the linear combination of predictive variables that are used to form the LDA decision rule, the Z-score. Now let's have a look at logistic regression. The logistic regression is a further development of normal OLS regression. The idea of logistic regression is now to adapt a logistic function that we see here to the point groups of solvent and insolvent companies. We see them here. So here we see the insolvent companies that have gone bankrupt during the year, and here we see all the points of those companies who have survived the year. The logistic function allows the following equation, and it looks like the following figure. Logistic regression belongs to a group of regression models known as generalized linear models. These generalized linear models have three common characteristics. First, there is a linear combination of the input factors. Second, the output follows a probability distribution that belongs to the group of exponential distributions. This includes the normal distribution, the Poisson distribution, and the binomial distribution. And the output distribution and the corresponding linear combination of input factors are connected by a so-called link function. In logistic regression, the logistic function is the link function. If we now apply the logistic function to the linear combination in order to produce the model output, we now see the probability of, let's say, a company belongs to the insolvent company, so epsilon is 1. I just remind you of the last picture where we had the 1 for the insolvent companies and the 0 for the for the surviving companies. And of course we model some kind of probability here. So if you have a very low equity ratio, the chance, the probability that you belong to the insolvent companies is very high, and it's dropping and decreasing the higher the equity ratio is. So the probability thus is modeled as the linear combination. We have it in the exponent here of the e, and here again, so the whole thing is back again, this function, right? And so this is the model output that is modeled here. So the left term gives the probability that the output belongs to class 1, the insolvent companies, based on the evidence of the input given. That is the x here, based on the evidence that the input is given. Thus, on the equity ratio given. For the logistic regression, the underlying probability distribution of the output is the Bernoulli distribution. This is the same as the binomial distribution with a single trial, and is the distribution obtained in an experiment with only two possible outcomes having constant probability, such as a coin flip. The mean of the Bernoulli distribution, mu epsilon, is the probability of the outcome class 1, which means insolvency. Consequently, the left-hand side in the previous equation is also the mean of the underlying output distribution. For this reason, the function that transforms the linear combination of our input features is sometimes known as the mean function. Now, to determine the link function for logistic regression, some simple algebraic manipulations can be performed in order to isolate the linear combination of input functions. So here again we have the same function that is also called the mean function. And now we start some algebraic manipulations. We simply isolate the linear combinations here. So the first thing that we do is to multiply with e in the power of the linear combination plus 1. So both sides multiplied gives this one. Then we're going to exclude the 1 here, of course, by multiplying out the brackets. Yeah, and just after some steps we arrive here. So here we have already isolated the e in the power of the linear combination, and on the left side we have what we call the odds ratio. The odds ratio is the chance, not the probability, but the chance. So here we have the probability of becoming insolvent, and here we have the probability of not becoming insolvent. So this is the odds ratio or the chance. And now by taking the natural logarithm on both sides, we end up having isolated the linear combination here. And the natural logarithm of the chance, that is called the logit. And that's where the name comes from. So this is the link function of logistic regression. It is called the logit. And this part of the formula is also called the logit. That's why we also speak of a logit regression. The term on the left-hand side is known as the log odds or logit function and is the link function for logistic regression. The denominator of the fraction inside the logarithm is the probability of the output being class 0 giving the data. Consequently, this fraction represents the ratio of probability between class 1 and class 0, which is also known as the odds ratio. If you look at the right side of the last equation, you can see that it has almost the same form as a simple OLS regression. Only the left side corresponds to the logit function, so that the regression coefficients cannot be interpreted the same way as with the OLS regression. In logistic regression, increasing xi by 1 unit multiplies the odds ratio, i.e. the fraction inside the brackets, by multiplication of e to the power of beta I. So if the coefficient beta I is positive, then we multiply the odds ratio by a number greater than 1. In other words, increasing the variable xi effectively increases the probability that the observation unit belongs to class 1. It is the same if the coefficient is negative. Okay, I'm back in our studio and I just want to show the part for the logistic regression in my code. The first part here is just the beautiful chart that we've seen before. To achieve that, first of all, in line 100, I have to turn the default into a number between 1 and 0. That's it, and I just plot it, and I achieve, or I get this beautiful chart that we have seen before. But now I would like to adopt the logistic regression as a generalized linear model. And because it is a generalized linear model, we apply GLM. So there is no specific code for logistic regression, but we need to take GLM, generalized linear model, and we model the default depending, so the yes or no default, independence of the equity ratio and the current ratio here. But what makes the generalized linear model a logistic regression now? Of course, the family, so the family of distributions and the link. So we have to change the family parameter to binomial and using the logit link function. Binomial distribution and logit link function. That makes a generalized linear model a logistic regression. And I just make some output and we see that we have an intercept. So seemingly we have a significant intercept. We have an equity ratio here that is highly significant, 3 asterisks, minus 24. So with increasing equity ratio, the chance of becoming insolvent or bankrupt decreases. And with increasing current ratio, the probability of bankruptcy falls too, and that is still significant here. So very interesting and nice output here. We can also make a vector of predicted probabilities. To achieve that, we use the predict command again. And just run this on the model type is response. So, oops. We get a vector for that. That will also be written into financial reports. So in our data here, we can make a vector of predicted classes by cutting off the response, by cutting off the probabilities at 0.5. So if we look here at 0.5, everything with a value above will be will be has the risk of becoming insolvent, and everything below will not. But of course, this is an arbitrary cutoff point at 0.5. We can also use 0.25 or 0.75 or whatever we like. We just decide here that every company with a probability higher than 0.5 is at risk of becoming bankrupt. And we can now assess the accuracy by having a frequency table here. So we have the real defaults here on the left side, and we have the model defaults here on top. So these are here we have the model defaults, and here we have the real defaults, false and true. So and we can see that there's obviously a connection between the model prediction and the real world. And the ratio of right predictions then is 0.97. So our model has a 97% accuracy. So that's beautiful. Those of you who are in my course, I would like to ask you also to try out this artificial neural nets for classification. But I'm not going to go into this in this video because the video would be much too long. So have a try with this one. You got the code if you like. I'll just scroll down the code for all others if you like. So thank you for watching this video, and see you in the next video.